Yeah, so that's something that I saw in the book. Essentially, they want to derive this expression for, do you have the book with you?
Yeah, I have a photocopy of book.
Chapter 2. Perfect, yeah. Yeah, so they derive. Yeah, this part, okay. So they're like, you know, we can talk about a specialty group where all the structure constants are 0, right? So,
Abelian
and they
case,
say,
yeah.
yeah, it's abelian, that's the abelian case.
Right.
They're like, all the generators commute. And then they're like, so it's easy to calculate what the unitary should be. You just do this thing where you raise it to the power n, like you did the other day.
Yeah.
And they do it. But they say they use the notion of
Yeah,
abelian.
I don't understand why he did that.
Okay, so it is true that any element of the Lie algebra can be written in the form of this equation here at the bottom.
Written the way I did it, yeah.
Oh, the way you did it. Okay, yeah. Look back to the
All right, good question.
physical math.
In fact, I'm going to review the Lie algebra stuff again because it's of really crucial importance. And also because I think things on, right?
Yes.
Because I think Weinberg's notation was, Weinberg's way of doing it was rather complex. He has an extraordinary ability to appreciate the significance of symbols. And I am out of normal chalk. I'm going to have to use big chalk. I guess then, since it's time, and since the camera's rolling, I'll start now. So as I said last time, the generators of a representation are the partial derivatives in other words, we have a group, G. There are elements of the group which we label by parameters. These are elements of the group, and we have a group multiplication law. G of alpha, G of beta is some G of gamma of alpha and beta. Alpha are the parameters for element G of alpha, beta are the parameters element G of beta, gamma are the parameters of the product. And we're going to be, and some books on group theory stay with the group elements. The cool thing about Lie algebra is that you talk about matrices rather than abstract group elements, and in fact, what you have is you say DG, you have a map from the abstract group to matrices, which I'm just going to write as D of alpha. And that's one representation, but there'll be many representations. And all the representations have to be faithful to the group multiplication law. And the cool thing about Lie algebra is that you can consider infinitesimal tiny values of alpha, and then this is I plus a sum alpha A TA, where these are the generators. And A goes from 1 to however many generators there are. Now, there's a summation convention that is just designed to avoid all the sum signs. And in that summation convention, we just sum over repeated indices. In general relativity, you've got upper indices and lower indices, and you sum over repeated pairs, one upper, one lower. Here, we're just summing over any two indices that happen to be repeated, whether they're upper or lower. And so this is a representation true for tiny alpha. And if we in fact write alpha as make it explicitly tiny by writing it this way, and here I'm using the summation convention, this becomes exact in the limit n going to infinity, and then we can recover d of alpha as the limit n goes to infinity of alpha a over n ta raised to the nth power. And of course, this is just e to the I alpha a ta. So this is called the exponential parametrization of a Lie algebra. And it's the normal and convenient way of writing group elements. And in fact, you can then go from, you then have three things. You have d of alpha, which is representation of the group g of alpha, and then you're representing this group element and the matrix d of alpha. You can represent that by a unitary transformation u of alpha. So this is unitary, and this is in Hilbert space. This is n by n, and it's unitary when the group is compact, not unitary when it isn't, and this is abstract math. So the G's are only on the south side of Lomas. Here we deal with the matrices and the unitary operators. Now, let me review the derivation of the structure constant business because it is so important. And I've rewritten and I've put on the class webpage a new version of my notes for the group for Lie algebras. And I also put a link to Sidney Coleman's lectures. Sidney Coleman was a remarkable professor at Harvard who gave his main course that he taught almost every year was on quantum field theory, a two-semester course, and it was a magical course. And in fact, he told us, I was a student in it back in the 60s. Anyway, he told us once, or somebody told us, I think he must have told us, that when he was in high school and probably college, he had magic as a hobby. And that showed up in his lectures because he would do things in a kind of showman-like and magical way. The advantage of that is that his lectures are fun to watch. The disadvantage is sometimes he uses magic to distract students from the nasty points and just skipped over. So he would help students to leap over difficult parts by using magic tricks. Weinberg does the opposite. He tunnels right into the difficult parts and uses no magic. On the other hand, both are among the best writers. Sidney Coleman unfortunately died of brain disease prematurely. In a sense, every death is premature. Some are more premature than others. Anyway, we can consider special cases of these formulas, in particular where we just have a single group, a single generator. So we might have d of alpha as e to the I epsilon TA. So in other words, we choose the alphas so that alpha sub I, say, is epsilon delta IA. And we can choose d of beta e to the I epsilon t beta, TB, by saying that beta, it's supposed to be a beta. This is going to be a demo of the Lorentz Group. Beta J, say, is epsilon delta JB. And so then these elements, these correspond to, of course, the group elements G of alpha. These correspond to the group elements G of beta. And then there are going to be inverses, d inverse of alpha, which would be just e to the minus I epsilon TA. And this corresponds to G inverse of alpha, which is also G of minus alpha. And also we would have G inverse of beta, would be e to the minus I epsilon TB. And that corresponds to G inverse of beta. Okay. Now the multiplication laws of the group are such that, let us say, G of beta times G of alpha. Remember, alpha and beta are infinitesimal exponential parameters. And over here, I use gamma for the parameters that occur when you multiply group element G of alpha for arbitrary alpha. G of beta, arbitrary beta, you get some other one, G of something, and I called it gamma. Over here, I'm going to say that this is G of gamma of alpha and beta, and this gamma refers to this particular product of 4 abstract group elements. And then, consequently, the matrices D of beta, D of alpha, D inverse of beta, D inverse of alpha, or equivalently D of minus alpha, D of minus beta, have to be D of gamma of alpha and beta. And if we have any other representation, then D prime of beta, D prime of alpha, D prime of, let us just write this as minus beta, D prime of minus alpha, is D prime of the same gamma of alpha and beta. Is this blocking your view?
No, it's not.
Okay. So this is the key thing. This is the abstract group element. A representation of a group has to faithfully represent the product law of the group. And so if the group does that, each representation, D, D prime, D double prime, and so forth, all have to do these things. So now, if we go to the case of, the simple case of each of D of alpha being just e to the I TA and D of beta e to the I epsilon TB, epsilon being very, very small, and just multiply this out, EBI epsilon TB, EBI epsilon TA, e to the minus I epsilon TB, e to the minus I epsilon TA. This then, if you multiply it out, I should have made this a homework problem, but it's approximately 1 plus I epsilon TB minus epsilon squared over 2 TB squared, and then it's times all these other things, so I would have to write it this way, times 1 plus, yes, 1 plus I epsilon TB minus epsilon squared over 2 TB squared, 1 minus I epsilon T, wait a second, what am I doing here? I've got to get the B's and the A's straight. B, this one was an A. This is the second one. This is B. Okay, so in the second order, you multiply all this out, you drop terms of third order and fourth order, and what you find is that all the terms of first order cancel, and many of the terms of second order cancel, and what you get then is 1 plus epsilon squared TA TB minus TB TA. And I'm going to write that as 1 plus epsilon squared, the commutator of TA with TB. So in physics departments, we use TA bracket TA comma TB square bracket to represent this structure. But now, this was the representation D. For the representation D prime, we would simply have e to the I epsilon TB prime, e to the I epsilon TA prime, e to the minus I epsilon TB prime, e to the minus I epsilon TA prime. And this would be the same structure but with primes, and so we would have T prime A, T prime B. So these TAs might be 2 by 2 matrices, the T primes might be 3 by 3, 4 by 4, whatever. And on the other hand, these have to equal d gamma of alpha and beta. And d gamma of alpha and beta approximately have to be like this, 1 plus epsilon squared times something. And the something, since I'm using a summation convention, I can use this as F C A B T C. And then d prime of gamma of alpha and beta, well, it has to be the same thing, 1 plus epsilon squared FC AB, but now T prime C. It's going to be really hard to write with this chalk. And so what we have then is, the relation that the commutator of TA with TB is FC AB TC, and the commutator of T prime A with T prime B is the same FC ABs, but now with TC prime. And so this means that for all representations, we have TA, TB equal to, you see I've got a typo in the notes here. I FCAB TC,
And then, for example, T prime A, T prime B,
I FCAB T prime C, and
you could go on indefinitely, T triple prime A, T triple prime B,
I FCAB T triple prime C. So that's the Lie algebra, and these things, these F's, are called the structure constants. And they're the same for all representations. That's the point of this long derivation, that the F's are the same. And the F's are the same because all representations have to respect the the multiplication law of the group. So any questions? Yeah.
Should be eyes on. I should have known that. Should be eyes on these final results here.
Excuse me?
So I can't do that expansion in my head that quickly, but if the commutator is equal to I times this.
Yeah, there's, okay. I left out an I here. There was an I that I should have put in. When I was doing the notes, I just was sloppy. There's an I here. Now, why is there an I here? There's an I here because of the way we set up here. Let's look over here. The generators are minus I times the group element, the matrix, the derivative of the matrix with respect to the parameter times minus I gives you the group element. Equivalently, gives you the generator. The representation of the group element corresponding to the parameters alpha, if we're near the identity for infinitesimal alpha, is the identity matrix plus I, real parameters alpha, and then matrices TA. And I guess I neglected to say that the alphas are real. The alphas are real by convention. If we needed another, in fact, in some cases we do need, it would be as if we had complex alphas. What we have is we have a different generator, but we keep the alphas real. And so consequently, since gamma represents a group element near the identity, D of gamma has to be 1 plus I, something small, something real. This has to be real times the T's, the generators. So that's how it works.
Are they only real for the case of compact?
No, we're general here.
Okay, it's totally real.
But we haven't said that these are Hermitian.
Oh,
These are
okay.
not necessarily
Yeah.
Hermitian
I
in
see, I
general.
see, I see.
And in fact, we're going to be, I'm going to have to go to Costco and get some more All right, well, these T's, you can multiply them by constants and so forth, and you can make them orthogonal, and so you can have the trace of TA with TB with some K delta AB. So you can make them orthogonal, but because they all have to have the same structure constants here, the K varies with the representation. So this is representation dependent, the K. And we have this multiplication law. If we multiply it by TD, we have
TA, TB, TD say is I, FC, AB, TC, TD. We take the trace, this thing gives us IK, FCAB, I'm sorry, FCAB, yes, delta CD. And so this is I, K, FD, AB. So now we have a formula for FDAB. FDAB is then, let me just copy it from the notes. It is minus I over K trace commutator TA with TB, and then TD adjoint. Okay, I made a mistake. When I say you make them orthogonal, what I meant was you say that TA with TB adjoint is orthogonal. And so I multiplied here by TD adjoint. We have TD adjoint. And right, okay. So the rest of this is right. I normally warn students that if I'm lecturing with my left hand down, and my left hand always holds my notes, then there might be typos. And so you have to watch very carefully what I write and say if the hands are down. If I'm having the thing up and reading, then it's normally right. Okay, so this is the correct formula, and now we can see that this thing is anti-symmetric in A and B because the commutator is anti-symmetric in A and B. And so what is our general matrix? Our general D of alpha then is E to the I, alpha A TA, summed over A here. And you can see that if the TAs are Hermitian, this is a unitary matrix. But if some of the TAs are anti-Hermitian, then this is something that's not unitary and it can get very big or very small. And why would the thing get very big or very small? That's if it's representing a group whose elements can, in some sense, get very big or very small. And those are non-compact groups. So, for example, the Lorentz Group is non-compact because the boosts can take a particle from momentum 0 to a momentum that's arbitrarily large. Or can take a momentum that's arbitrarily large, bring it down to 0. Okay. Now, compact Lie groups, on the other hand, if the T's are Hermitian, then the group is compact. So the group is compact. The D's are unitary. And let me just put that in the bubble because it's not the general case. It's just a case for compact groups. And in this case, FCAB is minus I over K times the trace of the commutator TATB TC, because you can forget about the adjoint because the thing is Hermitian. And now if you use the cyclic property of the trace, what you can show is, I'll maybe do one of these, but I don't know want me to do all of them. It's then the trace, of course, of TA, TB, TC minus TB, TA, TC. And now you can write that as minus I over K trace. And now you can move the C's forward, say. So, so let me see, what did I do?
Oh, yeah.
Oh, I didn't do it that way in my notes. So,
Did, oh, Kevin?
let's, well, you could move, say,
Kevin, you're forgetting an adjoint. On the TC, you're forgetting an adjoint, right?
no, I'm talking about the compact case here.
Oh, okay, yes, it's from issue.
So, compact here.
Okay.
And let me follow my notes so as to make things simpler here, otherwise I'll get everything balled up. So let's consider FB AC. And this is, if it's FBAC, this is TA, TC, TB, minus TCTA, TB. And now one can rewrite that as TATCTB. Okay, that's what I wrote there. You can rewrite that as TB, TA, TC, moving the TB forward, and then moving the TC backwards. So you take this guy and move him forward, and you take this guy and move him that way. And then you've got TB, TA, TC minus TA, TB, TC. And now this one is actually minus I over K trace of TBTA, TC. And so this is FCBA. And so what one shows eventually is that FABC is equal to FCAB is equal to minus FCBA. Well, this is just true for any group. And then also FCAB is FBCA minus FBAC. So it's basically totally anti-symmetric. And so then what one does is one just says that FCAB, you can just write this as FCAB, which is the same thing since it's totally anti-symmetric as FABC. So for compact groups, one can just write the thing this way, all indices down, and it's totally anti-symmetric. Totally anti-symmetric. That's only the compact case, though. And they're totally anti-symmetric and real. To see that the F's are real, well, F star ABC is I over K trace of TATB TC, but this thing complex conjugated. I already complex conjugated that. And when we complex conjugate that, what we get is minus I over K trace, and these are all Hermitians, so this just becomes TC, TBTA, and altogether this turns out to be, where did this minus sign? There was no minus sign here. then what we see, we can always put the C here, the TC there, so we can say it's I over K trace TBTA TC, but now if we interchange B and A, we get minus I over K trace TATB TC, which is F ABC. So for compact groups, the structure constants are real. A moment ago, I said the structure constants were also real for non-compact groups, and I guess that's wrong because the proof here is for compact cases. But I don't know, maybe one can prove that the structure constants are real also for the non-compact case. I don't quite see how that's going to work though, because when you take the complex conjugation, everybody here would get an adjoint sign, and that looks like a more complicated argument here. So this is, so the fact that, so that I think maybe it's just that they're real in this particular case, they seem to turn out to be real. Because if the thing is very close to the identity, then it's I times something real times a generator, sum of the generators. So right there, it looks as though those are. They look. All right, I'm going to leave that aside. I will think about that before class next time. And in fact, I can make that an extra credit problem. Figure out whether one can choose the structure constants real, whether the structure constants are real, even if the group is non-compact. In fact, you could perhaps Google the thing and find the answer. All right, well, last time, here.
Oh, sure.
Last time, there's another bag. Last time I worked out the rotation group, and I don't think there's, well, I'll repeat the result of that, and then give a demonstration of that relation here. So the rotations, of course, are, or I should say, the orthogonal group is a group that in n dimensions leaves the sum of the squares of the variables invariant. Oh, and I forgot to say something last time when I was talking about quantum mechanics being, some of quantum mechanics being, in a sense, common sense, or something that could equally well describe classical physics. I didn't mention, I forgot to say something, namely that, you see, in quantum mechanics, we have the probability of some state of a system known to be in state psi being found to be in state phi, we say this is the absolute value of the inner product squared. What's not obvious is that it's squared. And the reason why it has to be squared is that you can imagine, as we often do, we divide the Hilbert space. We can expand any space, any state in the Hilbert space in terms of a set of orthonormal unit vectors. And then we would want this to be phi I squared psi squared. Summed over I, we would want this to equal 1. So this sum P of phi I psi should be 1 because the sum of it being in any of the complete orthonormal states should be 1. And you can arrange that if, of course, these are unit vectors, they're complete, and you can have the sum of the squares be 1, but it's not natural to have just the sum of the absolute values to be 1. In other words, this is a Pythagorean theorem. So we're talking sum of this squared plus this squared is equal to that squared. And then n dimensions is the equivalent thing. So that only works if you take the probability as the absolute value square of the inner product. So the rotation group then is such that X transpose R transpose Rx equals X transpose X. So R transpose R is the identity. So in the Lie algebra sense, we let I equal, let me just glance at the notes here, in case I keep the same notation. Okay. This would be I plus omega transpose, I'm sorry, I plus omega, and so this is I plus omega transpose I plus omega is 1, and this is approximately 1 plus omega transpose plus omega, and omega being tiny, and so we say that omega transpose is minus omega. And if we're in 3 dimensions, there are exactly 3 of those things, and I wrote them down last time. Omega 1 is minus 1, 1, all the others being 0, and so forth. So I wrote them down last time. I don't think we need to do it again. The Lie algebra then is if we set TB as minus I omega B, there are 3 of them, and then TA with TB is I. The rotation group is obviously compact, so we can write this as ABC TC. It turns out that these F's are just the totally anti-symmetric Levi-Civita 3 symbol. So epsilon 1, 2, 3 is equal to 1. So this is what represents rotations. Rotation is then e to the minus I theta dot t. There are 3 t's, so we can think of a vector of 3 by 3 matrices. And this represents, or if we just rewrite it as e to the I theta dot L over h bar, we're just setting L equal to h bar t. So this is h bar, not trace. So now I can do this demo. Namely, we can think about
a, I'm trying to keep these things straight because I don't know which ones work and which ones don't. So let's do what I erased, namely, let's consider e to the I, well, that doesn't work very well, does it? Let's try this. E to the I e to the I, that's even worse. Okay, I think this one has to be retired. So that's e to the I Ly over h bar, e to the I Lx over h bar, e to the minus I Ly over h bar, e to the minus I Lx over h bar. Or equivalently, the same thing with just calling this ty tx, ty tx. And this is approximately then 1 plus epsilon squared over h bar squared commutator of Lx, Ly. And in quantum mechanics, we say Lx, Ly is I h bar Lz. So this should be 1 plus epsilon squared I over h bar Lz. So this should be a rotation in the minus direction about the z-axis. So now let's verify experimentally these Lie algebra relations. So what are we doing? We're doing a rotation about a right-handed rotation about the x-axis, right-handed rotation about the y-axis, inverse of the right-handed, or equivalently left-handed rotation about the x-axis, left-handed rotation about the y-axis. The product of all four in that order should be a left-handed rotation about the z-axis. By the way, there's a typo in the version of Weinberg's book that I got from the web has a typo in, to put it differently, his rotation operator is a left-handed rotation as opposed to a right-handed rotation. All right, now I want to do this for you. Can you turn the thing? Now, I haven't done this in several months, and all right, let's just start out like this. Okay. So the x-axis is this way. The y-axis is out toward you, and the z-axis is vertical. I think that's a stable z-axis. Okay. Now, these relations become exact if I do rotations of 1 second of arc, but of course, if I do rotations of 1 second of arc, you won't see any effect at all. So I'm going to do bigger rotations. And the first is then a right-handed rotation about the z-axis, x-axis. The x-axis is that way, right-handed is this way. And so I'm going to basically do that. Now I want to do a right-handed rotation about the y-axis, which is pointing toward you. And so let me just put a mark on the top so I get some idea of what the distance is here. Roughly like that. That's the
right-handed rotation about the y-axis. Now I want to do a left-handed rotation about the x-axis. The x-axis is still pointing this way, so I'm doing a left-handed rotation about this one. And maybe I'll put a mark there. Okay, that's the left-handed rotation about the x-axis. Now I'm going to do a left-handed rotation about the y-axis. Is that? Oh, screw! I made it wrong. L, X, L, Y. I just did left-handed rotation about the x-axis. Now I have to do left-handed rotation about the y-axis, which is this way, which means I go that way. I hope I did this right. No, it's right-handed would be this way, so I'm going to do this. Roughly like that. Well, I think this is a left-handed rotation about the z-axis, but it's
actually pretty good.
You think it's pretty good?
Yeah, because you have the y-axis directly out here, and all you did is just rotate it there.
Let me do it one more time, and this time I'm going to start out with this being the y-axis and this being the x-axis. So, all right, so right-handed rotation about the x, so that means I do this and that. Now, confusing. Right-handed rotation about the y-axis going out that way. Right-handed rotation about that. Now a left-handed rotation about the x-axis. And now that's the y-axis. I want to do a left-handed rotation about that. Oh no, it's this way, isn't it? Thank you, thank you. Well, that's a little more convincing because this was the y-axis initially. And so this is a left-handed rotation about the z-axis. All right, well, does anybody want to do it himself? All right, you see me get confused so much that you don't want to take the chance on camera of screwing up. All right. Okay, so that is the rotation group. Now let's jump to the Lorentz group. On the notes that are online, there's a big gap in pages, maybe 20 pages that you skip to go from you go from the rotation group to the Lorentz group. So now for the Lorentz group, what we've got, well, let's see, I can do a little more on this board. By the way, does anybody know anything good to watch on Netflix? The best things we found were Australian, Wanted and Rick. Most of the stuff is just junk. They call it content. Well, this is not the way to write on the board. Let's see if this works. So for the Lorentz group, XY is That's the idea of a Lorentz group. And, but what we've got here is eta, where eta is the flat space metric. So eta is -1, 1, 1, 1. Zeros everywhere else. And so what this says is that eta is equal to L transpose eta L. So any 4x4 matrix that real 4x4 matrix that does this is said to be a Lorentz matrix in the Lorentz group. And sometimes this is written as 031 or 013. I'm not sure which is more common. Since we have this relation here, it's clear that eta squared is 1. And consequently, we have here eta squared is eta L transpose eta L. And so that means that eta L transpose eta is L inverse. And so what is this relation? Let L be 1 plus omega, where omega is infinitesimal, then this requirement is eta is 1 plus omega transpose eta 1 plus omega. And so this is eta plus omega transpose eta plus eta omega is 1, dropping the omega squared terms. And so what we get is that omega transpose eta is minus eta omega. Or equivalently, that omega transpose is minus eta omega eta. Now, what this tells you here is that omega can be written as 3 real parameters dotted into the 4x4 analogs of the omegas on the other side of the board, plus 3 real parameters dotted into 3 new 4x4 matrices. And so let me write down what R1 is. R1 is all zeros, minus 1, 1, 0, and everybody else 0. The R2 and R3 are similar things where the bottom 3x3 matrices are just the omegas that I wrote down on Tuesday. On the other hand, the boosts are these. B1 is 0, 1, 1, 0, everybody else 0. B2 is 0, 0, 1, everybody else 0. B3 is 0, 0, 0, 1, 0, 0, 1, everybody else 0. So it's curious, the boost matrices are actually simpler to think about than the rotation matrices, which have minus signs.
So when you're at the top left hand, should that be X transpose eta Y?
I'm sorry, where?
Top left of the board. Is it no, up? Is that?
Yeah, sure. Yeah, absolutely. Yeah. I just left it out. Yeah. Okay.
Could you explain the form of omega again?
Say it again.
Could you explain why omega looks the way it does? Why it's theta r plus lambda b?
Okay. All right. It's explained here in the notes, and frankly, it's something that requires some puzzling over. But the idea here is, you can imagine some arbitrary matrix omega. You multiply it by your eta. The eta has a minus sign here, otherwise it's ones. Okay. What you can see from this is that under transposition, the time and the space elements of omega, this is transposition. The time and the space elements of omega change sign, while the time space and space time elements of omega under transposition do not change sign. Now, and so that's what you have here. Here, these are time, space, time, space, time, space. They don't change sign under transposition. Whereas over here, this is space, 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 space. Under transposition, they change sign. And so that's how it goes. And now that I think about it, when I say time, the time would be the 0, 0, but if that changes sign under transposition, it has to be 0. So it can't change. I mean, it changes sign, but you can't see the change to 0.
It's
Actually, you
yeah. So yeah. Why do these things have to be traceless, by the way? What's the reasoning for why these generators should be traceless?
Did I say traceless?
Well, I mean, they just are. I don't know. Yeah.
They are traceless, and almost always one wants things to be traceless. Now, why?
Being traceless would make it determinate.
Like if omega is identity, then the left. If omega is identity, then the left part is 1, right part is minus 1. Then if there is anything diagonal, then there will be A equals to minus A.
It's certainly consistent for them to be traceless. It's consistent to be traceless because you've got an omega on both sides.
Yeah. I think, yeah, but you remember saying, I guess, that this relation says that it says that the diagonal elements should be equal to negative themselves. Because the conjugation by eta is the diagonal matrix itself.
Okay, so all right, that would be like this. Omega transpose I is minus eta I j omega j k omega k I. But on the other hand, this thing is diagonal, so this is minus eta I omega I eta I. And this thing squared is 1, yes. So this is minus. So, on the other hand, transposition doesn't do anything to something on the diagonal. Okay, very good. So you each get.
Oh my.
At least it's not tea. Tea stained, whereas coffee comes out in the wash. Nice coffee, though. Good point. All right, so those are the Lorentz matrices then, and now here's the remarkable thing. You might think that the representations of Lorentz Group are very complicated. In fact, they're not nearly as complicated as, I don't know where that came from, as you might think that they are. And that's because of a remarkable property of the, let me see if I can just get an ordinary piece of chalk. It's really hard to write with this big chalk. Anyway, we have this L as I plus omega, and we're saying that this is, it's 1 plus theta, let us say theta L, RL, sum from 1 to 3, plus lambda L, BL, sum from 1 to 3. And now what we're going to do is this usual thing in physics departments where we stick in i's, and so this is going to be 1 minus I theta L, IRL, minus I lambda L, IBL. And now if you remember what the R's were, they were real and anti-symmetric. You multiply by an I, now they're imaginary and anti-symmetric. That means Hermitian. So these are Hermitian. These were real and symmetric, now they're imaginary and symmetric. That means they're anti-Hermitian. So boosts are anti-Hermitian. And what we normally do is we rename these. We call these JL. And we call those KL. What am I doing? I really should keep my left hand up. Now here's what's really, well, let us just say you form the commutation relations. What you find is this. So you find that the J's, as you'd expect, are just satisfy the commutation relations of angular momentum. You then find that Ji with Kj is I epsilon ijk kk, and this just tells you that the three k's are a 3-vector under rotations. That's reasonable. Here's the magic part. The magic part is Ki Kj is minus I epsilon ijk kk. No, not kk, jk. And so what this corresponds to, this commutator thing, this would mean that if we did a boost in the x direction, a tiny boost in the y direction, a negative boost in the x direction, a negative boost in the y direction, this would be equivalent to a small rotation about the z-axis. Now, that, I don't know, it's true, but it's not obvious to me. All right, so this is, I said there was a magical thing about the Lorentz Group, the Lie algebra of Lorentz Group. So if you have any 3 matrices, J, and another 3 matrices, K, that satisfy these commutation relations, they can be the generators of the Lorentz Group. And if you have any set JK, there's another set J minus K that'll do just as well. And you can see that because if you replace K by minus K, everything works out the same. All right, now, so before telling you what the magic thing is, let me just write what 1 plus omega or 1 plus theta dot r plus lambda dot b. This is 1, lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3. So this is an infinitesimal Lorentz transformation. 1, 1, 1 here, minus theta 3, theta 3, theta 2 minus theta 2, theta 1 minus theta 1. So that's what an infinitesimal Lorentz transformation looks like. And if we break it into time space, we can say this. The t prime is t plus lambda dot x, and x prime is x plus t lambda plus theta cross x. I'm using, this is just the ordinary cross product, but since we've got an x here, I don't want to have two x's. So if you want, you can write it as theta cross x, but it's a little funny. I have a phone somewhere. Yeah, hello? It's my wife, I have to answer. Hello? Oh, okay, I can be, oh God. Listen, why don't you just drive home and relax? I'm still teaching. Bye. I asked her to pick me up, but I thought she was going to be here after 7. Okay, so what is this Lorentz matrix? This Lorentz matrix then is E to the minus I theta dot j minus I lambda dot k. Now, here's the magic. 4 minutes of magic. You define JL plus or minus as 1/2 JL plus or minus I KL. And you might say, oh, that's just silly, but it's not silly because it's remarkable what happens. You then get JI plus J plus J, I epsilon I J K, J plus K. You then get J minus I, J minus J, I epsilon I J K, J minus K. And then the one that is magical is J plus I, J commutator J minus J 0. So in other words, if you take these complex combinations of the rotation generators and the boost generators, you get 2 sets of new generators that have commutation relations that are independent and each satisfy the angular momentum commutation relations. But they're not Hermitian. Well, wait, this is Hermitian, that's anti-Hermitian, so they are Hermitian. They are Hermitian. And so that's a second set of magic. That means that we can have, I should say, yeah, they are Hermitian, but that doesn't really apply us that much. Anyway, let's recover the old J's. The old J, Ji is J plus I plus J minus I, and Ki is minus I, J plus I minus J minus I. So that's how you recover the original boosts.
What's the point of what's the point of giving these new generators?
Say it again?
What's the point of these new generators?
You mean the J pluses and J
Yeah.
minuses? Well, but they're remarkable because they now satisfy the commutation relations of angular momentum.
Oh, okay.
So consequently, you can construct representations that are just the representations of the rotation group. So the representations of the Lorentz group are like the rotations of the rotation group. So in particular, what we can have is that the general representation of the Lorentz group for parameters theta and lambda, well, they would be e to the minus I theta dot j minus I lambda dot k. But now, I just showed you what J and K are. So this is e to the minus I theta minus lambda J plus minus I theta dot minus I theta plus lambda dot J minus. And now J plus and J minus commute. So you can rewrite this as e to the minus I theta minus lambda dot J plus e minus I theta plus lambda dot J minus. And these matrices commute because the J plus and J minus commute. These things are beta commutation relations of the rotation group, and so what we've got here are essentially, we call this thing DJ 0 of theta and lambda times D0J prime of theta and lambda. So in other words, the general representation of the Lorentz group is the product of two matrices that are made out of the, are like the representations of the Lorentz group, of the rotation group. Okay, so we're basically out of time. So the J's obey the representations of the rotation group, but whereas this part, minus I theta dot J, that's unitary, minus lambda dot J is not unitary. And so when the lambdas are non-zero, these are non-unitary. So they're no longer identical to the representation of the rotation group, but they're very, very similar to those representations. And well, I'm really out of time, but maybe I can. Well, we'll pick up with this next time, and what I'll write down for you is how a quantum field then transforms, how an arbitrary quantum field of arbitrary spin transforms under a Lorentz transformation, which comes from these formulas, and then we'll drop back into Weinberg's chapter 2 and combine quantum mechanics and relativity and look at how states transform, and then jump, I think, to chapter 5, where we find out how fields should transform so that they transform, we can get them to transform the way that this implies. Okay, I think we can stop.